Entropy is the measure of the order or disorder of a system. And there's always some probability associated with the state in which you find a system. The probability of finding a system in a given state depends on what we call the multiplicity of that state. And the multiplicity is represented here by this letter W. This is the multiplicity. Okay? And so this equation here tells us the entropy of a system. The entropy of a system, represented by S, is equal to K, which is the Boltzmann constant. It's 1.38 times 10 to the minus 23 joules per Kelvin. And then we multiply it by the natural log of the multiplicity. So the multiplicity is the number of microstates corresponding to a given macrostate. What does that mean? Well, what is a macrostate? What is a microstate? Rather than giving you a definition, let us do an example to figure out what these two things are. So let's consider a system that comprises of 3 coins. Okay, so I've got 3 quarters here, okay? And the quarters can each have a head up or a tail up, okay? So the quarters can each be heads or tails whenever we toss them, okay? So we're going to think about the number of possible combinations you can have for heads or tails whenever you flip these 3 coins, okay? So whenever you flip these 3 coins, coin 1, 2, or 3, you could have all of them be heads. Okay? You could have 2 of them be heads and 1 be a tail. You could have 1 head, 1 tail, 1 head. You could have 1 tail, 2 heads. You could have, we could have 1 head and 2 tails. You could have a tail, then a head, and then a tail. We could have a tail, tail, head, and finally you could have all 3 of them be tails at exactly the same time. So we have 1, 2, 3, 4, 5, 6, 7, 8, 8 possible combinations for whenever we flip these coins, are they heads or tails? So this number 8 is equal to the total number of microstates. Okay. That's how many ways we can make these combinations of either heads or tails with our 3 coins. Okay, that's a microstate. So what about our macrostates? Well, let's see. We have 1 macrostate down here. We only have 1 way that we could get all tails. So that is 1 macrostate. And so we could say that the multiplicity of having 0 heads and all tails, so 0 heads, 3 tails. I'm going to write like this. The multiplicity of having 0 heads is equal to 1. Okay? There's only 1 microstate that will give me 0 heads and 3 tails. Okay? And then let's see, up here we have only 1 microstate that gives us, I'm going to write like this, 3 heads and no tail. There's only 1 of those. So this is 3 heads and 0 tails. Okay? And then let's look at these next here. We have here these 3 microstates right here. They all have 2 heads and 1 tail. So these are the different ways you can flip the coin to get 2 heads and 1 tail. So all of these possible combinations represent 1 macrostate. And for this macrostate, we could have 2 heads and 1 tail. Okay? And so I'm going to write that as the multiplicity of having 2 heads and 1 tail. That equals 3. Because there are 3 possible microstates, 3 possible ways that I can flip my coins so that I have 2 heads and 1 tail. Okay? And then down here is another possible macrostate. There are 3 ways I can flip my coins so that I have 1 head and 2 tails. Each one of these has 1 head and 2 tails. Okay, so this is 1 head, 2 tail. And so I'm going to write this as the multiplicity of having 1 head that equals 3, because there's 3 possible ways to get 1 head and 2 tails. Okay, so we've got 8 microstates. That's 8 possible ways that we could flip 3 coins to get either heads or tails. And then we have 4 macro states. Macro states. Okay? The probability of finding any given macro state is the ratio of the number of microstates within that macro state to the number of possible microstates. So what does that mean? So let's say the probability of getting n number of heads up in my flip here equals the multiplicity for the different ways that I could get those number of heads when I'm flipping the coin to the total number of microstates. Okay, so we saw that the total number of microstates here is 8. So this bottom number is going to be 8. And so this top number here will be whatever is the multiplicity of that state. So what if I asked you to find the probability of flipping all 3 of your coins and only getting 0 heads, getting all tails? So the probability of getting 0 heads is going to equal the multiplicity for the different ways that you can get 0 heads and all tails, divided by the total number of microstates. So in this case, 8. Okay, so I come over here, I saw when we were working through this that the multiplicity of getting 0 heads and 3 tails is 1. There's only 1 of 8 possible ways that I could get all tails and no heads. So the probability of getting 0 heads in this flip is going to be 1 out of 8, because 1 was the multiplicity here for us getting 0 heads and 3 tails. Okay, and so then there are 3 other possible combinations. So then you could also have the probability of getting 1 head, or getting 2 heads, or getting 3 heads whenever you do this coin flip. And so in the questions that I'm going to ask you for the pre-lab, you're going to get one of these 3 questions here. Okay, so this will be for question 5. Now let's suppose that we have 3 coins, my 3-coin experiment here, and we start with a very ordered system of having all 3 of my coins heads up. So I'm going to turn all 3 of my coins head up. That's this first macro state right here. Okay. What is the change in entropy of my system if I do a flip of the coins and I get 2 heads and 1 tail? So 2 heads and 1 tail, that would be any of these possible combinations right here. So this macro state, which has 3 microstates within it, this macro state would give me 2 heads and 1 tail. And there's 3 possible ways I can get 2 heads and 1 tail. So that means there's 3 microstates within that macro state. Okay, so what is the change in entropy of my system if I get 2 heads and 1 tail? And I'm going to write this equation as the change in entropy equals Boltzmann constant natural log of my final multiplicity minus Boltzmann constant natural log of my initial multiplicity. And actually what I'm actually going to ask you to do is report the quantity delta S over K. And so that equals our natural log of our final multiplicity of the system minus our initial natural log of our initial multiplicity of the system. So we've got 2 heads and 1 tail. So, and we started with 3 heads. Okay, so the multiplicity of my final system with 2 heads and 1 tail, come over here, I see there's 3 possible ways I could get 2 heads and 1 tail. So that's the multiplicity of my final system. So this is going to be natural log of 3 minus the natural log for the multiplicity of my initial system. So up here with my macro state, I see that for the possible combinations I can do to get all 3 heads within that macro state, there's only one possible way I could get all 3 heads. So within that macro state, there's only one microstate. The multiplicity of that macro state is only 1. So I come over here and I put in 1 right there. Okay? So then I take natural log of 3 minus natural log of 1, and that gives me 1.099 for this quantity of the change in entropy over Boltzmann constant. So this number is unitless. Okay? So if this number is positive, that means we are going toward a less orderly system. Okay? So we started with a very orderly system of all 3 heads, and then we increased the entropy of our system by going to a system that has more possible microstates. Okay? If the change in entropy is negative, that means you're going from a system that is less orderly to a system that's more orderly. So instead, let's say we started with our system here of 2 heads and 1 tail, which is less orderly, and then we moved to a system after we did our 3 flips of the coin, we actually ended up with all 3 heads. So we would be moving from a system that is less orderly to a system that's more orderly, and in that case our entropy would be negative, indicating we're moving toward a more orderly system, which is usually not the way that worked in our universe.